Alrighty, let's talk about torque. So torque, as far as you were concerned in physics 1, was R cross F. So that was like, if you have something that's R long and then you push on it with some force, it's going to feel a torque and start rotating that way, right? So it is still completely valid to use that. If you want to find the force on some wires and calculate the torque that way, you're still going to get the same answer. However, there is a specific version to save you some time for magnetism, and that's this equation here. So our torque is our magnetic moment crossed with the magnetic field that the thing is in. So our magnetic moment is current times the area vector. So we can determine the direction of that magnetic moment the same way we do field. So your magnetic moment is going to be pointing in the same direction as your field. So if I have a loop that's carrying some current this way, it's going to have a magnetic field out of the page from my right-hand rule. So my magnetic moment is also going to be out of the page because that's the area vector is determined that way. So area vector comes perpendicular from the surface or normal to the surface. So my area vector is pointing out of the page. And we choose to follow the direction of the current to get the direction of that. Because it could just as easily have been pointing in the opposite direction, but it's easier if it's in the same direction as B. Okay, so our torque is a magnetic moment cross B. So now let's say we take this loop and we put it in a magnetic field that's pointing that way. So my torque, I use my right hand rule, this one, because I got cross products now. My first vector is my mu, so that's going to be my pointer finger. Second vector is my B, and torque is my resultant, so that's going to be my thumb. So my mu is coming out of the page. My B is going up, so I'm going to feel a torque to the left. Torque. Now the direction of the torque tells you which way your loopity is going to spin. So that's going to be this right hand rule again. So if I point my thumb in the direction of the torque, my fingers are going to tell me which way this thing is going to rotate. So this is going to go this way, which we can double check by looking at the forces on this guy. So IL cross B is going to give me a force into the page at the top, and IL cross B is going to give me a force out of the page at the bottom. IL and B are parallel on these 2 points, so those aren't going to contribute. So my little loopity, let's see if I have a circular object. Circular object is going to rotate this way. So torque is going to rotate this way. And yeah. So let's look at another example. Let's say we have current carrying wire like this in a magnetic field that way. So my torque is mu cross B. My mu, if I follow my current, is going to be out of the page. So mu cross B. This is really hard to do. Mu cross B is going to give me a torque up, which means my thingy is going to rotate this way. So this one is going to go into the page, this one's going to come out, and it's going to rotate like this. Which we can double check looking at the forces on these wires. So my force on a wire is IL cross B. IL cross B. This wire is going to feel a force in. IL cross B. This edge is going to feel a force out, so it's going to start rotating this way, which is what my torque says. These two, IL and B, are parallel, so they don't contribute. Alright, so now we can, if you want to, you can also look at it this way, using the forces. So R, remember, is the distance from your axis of rotation. That would be that distance. So you can also just as easily calculate torque using R cross F. And yeah, not too terrible.